10 septillion years. That is 10 to the 25th power years. A number so vast, it makes the age of our entire universe look like a millisecond. That is how long the world's fastest classical supercomputers would need to run a single benchmark calculation. On December 9th, inside a high-security lab in Santa Barbara, a silicon engine did that exact calculation in under 5 minutes. Its name is Willow. But the raw speed is not why intelligence agencies and tech giants dropped everything to study this release. Speed in quantum computing has always had a dark secret: fragility. Until now, every time you added more power to a quantum chip, noise smashed into the qubits, corrupting data before it could finish. Google did not just build a faster chip, they built something once thought mathematically impossible: a quantum chip that actively heals its own broken data while running. Welcome to the opening salvo of the global quantum war. For 30 years, quantum mechanics had a fatal flaw. Normal chips use zeros and ones. Quantum chips use qubits, which can exist as both 0 and 1 simultaneously. That capability grants exponential processing power. But physical qubits are notoriously delicate. Stray magnetic fields, heat, or even a single stray photon will knock them out of state. It is called decoherence. For decades, adding more qubits meant exponentially more errors. The more power you added, the faster the system self-destructed. Then came Willow. Willow packs 105 superconducting physical qubits. But instead of running calculations on raw physical qubits, Google grouped them into logical qubits using surface codes. For the first time in human history, when Google increased the code, distance, the error rate did not explode. It dropped exponentially. They had crossed the threshold. But how do you fix errors that happen in fractions of a microsecond without looking at the qubit and destroying its quantum state? Now, here is the exact detail that almost every major tech news channel completely missed. You cannot measure a quantum state directly without destroying it. So, how do you fix a broken qubit inside a sealed cryogenic freezer operating near absolute zero? Google did not use hardware fixes. They deployed an AI sniper called AlphaQubit. AlphaQubit is a custom neural network that reads ambient parity check signals around the qubits hundreds of thousands of times per second. It does not look at the data. It listens to the acoustic noise of the system, predicts where an error is about to occur, and corrects the logical bit in real time. It acts like an autonomous digital immune system. While the calculation runs, the AI fixes broken qubits on the fly. The chip heals itself continuously. This is not just an academic triumph. It is a geopolitical earthquake. For years, IBM dominated with high physical qubit counts on their Heron and Condor architectures. Microsoft and Quantinuum staked their future on ion trap systems. China invested billions into state-funded photonic and superconducting platforms like Zhuchangji. Whoever achieves a fully fault-tolerant, self-healing quantum computer gains an unthinkable advantage. Modern global encryption, RSA 2048, the bedrock of banking, government communications, and military defense, relies on prime factorization problems that take classical supercomputers centuries to crack. A stable, fault-tolerant, logical quantum computer running Shor's algorithm can bypass that math in minutes. By proving that error correction works below threshold in real time, Google did not just advance research, they fired the starter pistol for the post-encryption era. The era of fragile, noisy quantum experiments is officially over. We have entered the era of self-healing silicon. The race for quantum supremacy is no longer about who has the most qubits. It is about who can keep them alive the longest. Is the world ready for what happens when modern encryption becomes obsolete overnight? Drop your thoughts in the comments below. If you want high-stakes tech analysis before it hits mainstream media, hit subscribe and switch on notifications. Thanks for watching, and I will see you in the next breakdown.